Good evening, everyone. Myself, Anchal Singh Thakur. I am your TA for this course, which is offered by Professor Singh Sir from IIT Delhi, and the title of the course is Power Quality. So this is our 11th session, and in this session, we'll be discussing a lot of just about a lot of topics that were covered in the last few lectures. So the last topic that we were discussing in the tutorial session was hybrid filters. So we'll carry
Madam,
on.
this is one more session is available, madam. This
Yes,
is
sir.
last
We
session
have
or
in total of 12 sessions, and this is the second last session.
okay, okay, ma'am.
Okay, so in this session, we'll be discussing mainly about mainly about a lot of AC to DC converters and then solar energy conversion systems, the converters which are involved in solar energy conversion system and wind. And so this is the few of the lectures that are remaining in the end. So So since a lot of theory content was remaining, so in today's lecture, I have planned only most of the theory content only. So let's see how it goes, and then we can discuss any questions if you have. So if in case you have any questions at the start, we can you can ask right now, or I'll proceed. Okay, then I'll proceed with the session. Okay. So, so far we started. So the title of our course was Power Quality, right? So we have been discussing a lot about the meaning of this term, right? What is the definition? What does power quality mean? Why is this topic so important that it is given the name of a whole new subject? Then we discussed about what kind of power quality problems exist. So we broadly categorize them into two categories: current-based power quality problems and voltage-based power quality problems, right? And then after framing the problem in front of us, that there is something power quality which is going to be very important in some time, and then we need to take certain measures in order to take care of this power quality problems. So now after defining the problem, we started to work on the solutions of that problem. So the solutions were broadly categorized into two categories. First was passive, another one was active, right? So the solution could be in the form of a passive kind of solution, or it could be an active kind of solution, right? So you could either form a passive filters or passive compensators are made up of R, L, and C elements, that is passive elements. Whereas active compensators or active converters are made up of R, L, and C components along with switches. So the presence of these switching elements make these active filters special. So these are like they are called as fixed kind of compensators because they are able to provide us fixed kind of compensation. Whereas active compensators have the capability of giving variable kind of compensation. That means they are more versatile than passive compensators. The only reason, yes, Sheikh, do you have a doubt? So I don't have like a proper clear idea about the exam pattern, but in most of the NPTEL exams, the standard pattern is similar to what questions are being given in the assignments. So definitely, since this was a very highly numerically based course, so definitely I think numericals will be there. And apart from that, theory we have covered very less theory, right? In almost, I think only your very few questions in your assignments were theory based. Most of the questions were numerical based. Okay, so mostly your paper will cover numericals, and it would be either integer type or it will be either MCQ type. But you will have to solve the numericals. There is no other alternative to that. Okay. Welcome. Okay. So let's come back to the topic we were discussing. Yeah, so we were discussing the solution of the about the solution of these power quality problems. So we discussed that we categorized the solutions to these power quality problem in two categories. One is passive type of compensation and another one is active type of compensation. So we all have seen capacitor banks, right? In most of the industries, we say that there is a capacitor bank put outside. It is very bulky in size, very huge, and it is very and they do it in order to maintain the power factor of the industry. Because in industries, if you don't maintain a particular power factor, then a fine is applied on you. So because of that thing, people take care of the power factor, and therefore they use passive compensation. But since we know that active compensation, we have been studying a lot of active compensators, right? DStatCom, DVR, UPQC. After studying all those things, now we know that they are better than fixed compensation or any kind of passive compensation. But still, the only reason people still don't use active compensation is because of cost. Believe it or not, most of the parameters in engineering are governed by a parameter called cost, which when we do theoretical studies, we usually don't give so much weightage to this parameter, but this is a very big player when it comes to decision making in while making engineering kind of decisions. So because of the only parameter, that is cost, active filters, although they are much more versatile than passive, they are not that widely used. So passive are still widely used. But as we discussed in few of the lectures, that because of the changing nature of the electrical load, our traditional electrical load were incandescent type of lamp, right? And then they were fans, lighting loads, very less, very decent kind of loads. They consumed beautiful sinusoidal wave type of current. But nowadays we have replaced these incandescent lamp with LED lamps, CFL bulbs, and the nature of current that these bulbs draw is highly nonlinear in nature. And because of nonlinear nature of this current, we have discussed in one of the lectures that because of this nonlinear nature of current, a lot of harmonics and the reactive power and all these a lot of power quality problems come into picture. And when these power quality problems come into picture, we need to focus more about solving these problems. Till now, our grid was highly driven by synchronous generators, and these synchronous generators have very high inertia, so they were able to hold the grid even in presence of these power quality problems. But now what is happening, from synchronous generator we are trying to move towards solar, wind, electric vehicles. So we are trying to we are in the way of a paradigm shift. What does paradigm shift means? Paradigm shift means when you try to change the way we look at things in the bigger picture. So far since decades we have been using synchronous generators and it was working fine. But now we have realized that there is climate change, and we have limited amount of non-renewable resources, and we need to take care of them. We cannot use them in an unlimited manner. Therefore, we got the motivation to move towards another sources of energy which are renewable in nature, and therefore we started shifting towards solar and wind and electric vehicles. We are trying to reduce the consumption of these non-renewable sources of energy. That is the whole motivation behind this shift. So now we know that we are in this arena, right? After 10 years down the line, maybe you will have a lot of, especially in south, if you look in south, a lot of almost every other house is having solar panel in their houses. So because of the nature of load that were initially not the nature of load that were present, because of the change in the nature of load as well as the nature of source, both the things are changing. So there is a simple source load system. You have a source, and that source gives electrical power supply to the load. Now we discussed that the nature of load has changed because of the front-end power electronics, elect, all the equipments that we have. If you just take a look around your room or wherever you are sitting, you will see your laptop, you will see a refrigerator, a CPU, a television, even the Bluetooth speaker that we have. Everything has power electronics inside that. And what power electronics do? Power electronics use switches in it. And because of the switches, what happens? We get intermittent kind of current, right? And it is not at all close to sinusoidal. So you know that this non-linear current has lot of harmonic components. And because of these harmonic components and the nonlinearity of these loads, the nature of load has, you know, changed a lot over the past few years, and it is going to change more as we go on adopting. Now only 10% of the population is having electric vehicles. Soon we'll move towards, you know, higher and higher percentage, and then everybody will want to charge them fast. So fast charging, then you know we'll be drawing very peaky currents. Then the grid will be the grid which was very inertial in nature. Now the dynamics of that grid is increasing, right? Because we are because at t equal to 0, suppose I am connecting 50 electric vehicles, and they are, and at t equal to 1 unit, all of them are disconnected. Then there is a sudden shift in electrical power, right? If I was consuming 10 watts, 10 kilowatts say before, then all of a sudden that 10 kilowatt became zero kilowatt, right? So this is a huge change in power. So therefore dynamics of the grid are increasing and the nature of load is increasing. And also we discussed that we are trying to change the nature of source also, from non-renewable sources of energy to renewable sources of energy. Because of all
Madam,
these
you are
things,
writing.
uh,
Madam, you are writing here a synchronous generator solar window. Okay, madam. What about the VV6 electrical vehicles, madam? That is.
basically I'm trying to say what are the changes happening. That initially we used to have synchronous generators and our traditional diesel and petrol vehicles. Now we are moving towards solar sources of energy, wind power generation. Then electric vehicle is a kind of load, right? Electric vehicle will be charged
Yes, madam.
using our grid. So this is electric vehicle will come in this category, right? Load
Okay,
category.
okay, madam.
And solar and wind will come in source category. So these are the changes that are occurring. And because of these changes in source load, and overall our, if you look at our electrical grid system, you can say in one way that the dynamics or the overall dynamics of our electrical grid system is changing, right? So therefore we need to take care of the new problems that are coming up, and most of these problems are studied under the tag name of power quality, right? So we have discussed a lot of solutions. We categorize the solution in multiple categories: for current-based power quality problems, for voltage-based power quality problems, and then for both these problems. So for current-based power quality problems, we discussed one example of an active compensator, that is D-STATCOM, right? Then for voltage-based power quality problem, we studied DVR. And as a and when if there is a situation where there is both current power quality problem as well as voltage power quality problem, then we studied UPQC, which is a combination of both shunt and series compensator, right? So we studied just one example of each. But in market there are infinite number of topologies that are coming up. There are a lot of products that are coming up. There are companies which are developed solely on the, you know, with the goal of improving power quality. So even there are Indian companies which are focusing on this area. So this is a very booming area that has come up. And as far as the theory is concerned, so we started with, you know, passive filters design. We designed the passive filter for current-based power quality problems. Then we studied active filter like DStatCom. Then we discussed a passive filter for voltage-based power quality problems. Then we discussed an active filter for voltage-based power quality problems. Then we discussed passive filter for both current and voltage-based power quality problems, and then we discussed the active solution. And then after, initially we started with focusing on power factor improvement and reactive
Madam,
power.
what is the major difference between filters and power filters, madam? There is only rating, madam. That is the
What is
only
the difference between filter and?
power filters.
Yes, we have discussed this before, right? So,
Yes.
so initially, when in the course we discussed about normal compensators, right? We use the word compensators. So when we use this word in the initial lectures, we focused on power factor and reactive power compensation and voltage regulation. Later on, we again came back to these problems and then we started calling them power filters. The only difference between these two is they here the main problem that was focused is harmonics. So there are you can call them compensators, filters, doesn't matter. At the end of the day, what problem they are solving, whether they are taking care of reactive power compensation or power factor improvement or voltage regulation or harmonics. So we have also seen few industrial examples that were focusing on all of these things. So you can call them either compensator or filter. The name actually does not matter. The only reason sir has, put them in compartments is in order to simplify your theoretical study. So you initially in the course we started with discussions about these three power quality problems, and then later on we introduced nonlinear loads and the problem caused by presence of harmonics in these loads, and then we started focusing on power filters, like designing filter with the goal of harmonics. We have also seen few numerical problems where the filter has to take care of both reactive power compensation and harmonics, right? The difference, the additional feature that will add is the rating, KVA rating of the compensator will increase, right? If we try to use same compensator for solving multiple problems, then the KVA rating of that compensator will increase, and so is the cost. Okay, so all these things are interconnected in one way. So after discussing power filters, we went to discuss hybrid power filters. So hybrid power filters are combination of passive and active solution. So they have lot of combinations possible. You could either use a passive shunt compensation or active series compensation or active shunt compensation or passive series compensation. There are a lot of topologies that we have discussed in the past tutorial session, and we also have looked at a lot of possible topologies and for these kind of hybrid filters. So you know the basic principle behind hybrid filters is they are a combination of passive and active. And why did we go for this combination? Again, cost. So we know that passive filters are cheaper, right? Compared to active filters. So when I replace a whole active filter with a combination of active plus passive, so suppose my this filter was 5 kVA rated. Now, if this filter is 1 kVA rated and the rest of the 4 kVA is my passive filter, then if suppose the cost of this filter is say 100 units, just assume that it is 100 units, then the cost of this combination will be approximately 50 to 60 units, which is very cheap, right? So therefore, that is the reason and this is hybrid. This is the reason we go for hybrid. Hybrid has become one of the most popularly used converters. So in order to save the cost and in order to provide a bit of a flexibility to the compensators, people have started using a combination of both passive and active. Okay. So again, while discussing the hybrid filters, we saw, right, that hybrid filters are nothing but just the simple combination of active and passive, and all the principles and the design rules that we derived for active and passive, same will be applied for hybrid. It's just a consolidation of all the things that we have studied before. Okay, so you can step by step, if you're thorough with your basics, the passive compensators and the active compensators individually, then you will be able to easily design hybrid filters and any other complex combination of that. Okay.
Madam, while designing active and passive filters, is there any ratio is there, madam? Percentage, they have to give this much of cost, they have to design passive filter for this much of percentage, like active filters, they have to design this much of percentage, like this. Any generalized percentage is there, madam?
No,
Practical.
sir. There is no generalization because the nature of load is not generalized, right? So every factory, if you look at, every factory has a different kind of load in nature, but they have periodic load in nature, right? So if you talk about a paper factory, it will have a certain load profile. Let me call it as load profile 1. And then if I talk about a cement factory, it will have certain different load profile, let's say load profile 2. Now these 1 and 2 are not same. They will never be same because they are having different kind of equipments and different kind of current ratings. So the consumption, maybe the shape might be same. Maybe this is, let me simplify it by saying that the paper factory is drawing quasi square current, and maybe cement factory is also drawing quasi square wave current. That may be possible, but will the current ratings be same? No, right? So therefore we cannot, and will these act in a same way over the time? No. Okay, so since the nature of load is not constant, therefore we cannot make any kind of generalizations into how much active and passive to node. But then a question comes, then how do you decide that, right? So as I mentioned before, whenever a company is given a task of doing power quality improvement at any industry or any location, what do? They first go to the site. Okay, site is the location. Suppose I am talking about a cement factory. Okay, so my site is a cement factory. So what I will, if I am the company and they have asked me to design a power quality improvement system for this company, what I will do is I will go to that company. I will look at the load profile of that company. What does load profile mean? With respect to time, this time will be, let me say, 365 days. I will observe that over the year, what happens? Seasons change, right? Then days change. So there is sort of a periodicity every year if you look at that approximately, every company will have certain pattern that they are consuming more in summer because they will be turning on all the air coolers and everything. So every company has certain periodicity that you can use to estimate this power quality equipment that you are going to put there. But you have to do this load profile study. So you do the load profile study. Okay, that from 12 a.m. to say 12 p.m. this is the current profile needed. Then this much current is needed. Then this much is needed. So over the 24 hours you will observe that. Then you will observe with respect to the change in season what is happening, in which month what kind of consumption is coming. So there is a whole new research area in which you do the load profiling. You can also predict the load based on the past consumption. You can predict that this company will have this much amount of electricity bill next year. You can do that. It is possible. Okay, so this load profiling, we go there and we do it. Then we do the PQ, like the active power, reactive power. We calculate. There are power quality analyzers. Power quality analyzers are there. If you put at the input of that factory, you can easily get these parameters, that what is the reactive power that this factory is consuming, what is the power factor. So based on this data and this analysis of the load that is present on that cement factory, based on that I will decide. So if I have a load profile like this, and my load profile is sort of constant for a lot of time, and only during one season it is having a peak. So if I can simplify my load profile like this, then what does this tell me? That I can put this much passive compensation and I can give active compensation for this variable part, right? Isn't it very simple to understand? So you know that this part will always remain, this much reactive power requirement will always be there. So I will put a passive compensator for that. And only this much power is variable. So I will put an active compensation compensator for this part, and I will size my active compensator only for this part. On the contrary, if I do just active compensation, what I will do is this peak, suppose this is 5 units and this is suppose 10 units. Then I'll have to design an active compensator for 10 units, which will be very costly, right? If I'm doing just active. So this is very expensive compared to this one. Therefore, we say that the hybrid combination is much more cheaper compared to the only active combination. Okay, and and since the nature of load is varying at every facility, therefore the solution also has to be customized. So what these industries, so if you go to an industry, what they do is they will design compensators for step size units. So suppose they will have a compensator for 5 kVA, then 10 kVA, then 15 kVA or 30 kVA, or depending on what size that industry is. Okay, and what is the need, what are the kind of orders that they get. So they have these variable rated compensators. So depending on what is the load profile at that company and what is the nearest sizing that is available with them. So they prepare a quotation for that rating, and that is how they propose to the industry that okay, this is how this much will be the cost of installing a combination of hybrid filter, and if you want to go for completely active, then this will be the cost, and then based on that quotation, the company decides which type of compensation they want. Okay, and all sorts of reliability studies are done, whether whether these equipments will be working for how long. Lot of engineering is involved in that, but this is the whole procedure of so there is no standard generalized solution for any power quality problem. You have to first look at the problem, and look at the kind of electrical load consumption or electrical power consumption, and then based on that electrical power consumption you can decide which kind of solution you want to take up. Okay. Yeah, so far we have been discussing about what we have discussed so far. Now let us move on to this week's what are the topics that are covered in this week. So in this week now we were looking at the solutions, right? So recently what in order to, again, this idea also came because of the cost parameter. Now what people said is there is this source, right? And then there is my load. Now sometimes during in my source to load conversion, there are, suppose my load is DC in nature, then I put a AC to DC converter, right? And so far the AC to DC converters that were available in market, anyways, so what I was doing to this, so suppose this is my system, right? I was having a source which was AC in nature and the nature of my load was DC, therefore I had to put an inverter. Now, if the power quality, if let me say that the power factor at the point, this, let me say this is point of common coupling, and at this point power factor is 0.7, which is poor, and I want to improve that power factor to approximately unity. Then what I will do is I will connect a shunt compensator, say, at this point, and I'll try to improve the power factor, right? So now in this case what I'm doing is already an inverter, let me call it 1. Already inverter number 1 was connected to the system, and then I added another shunt compensator 2 to the system. So in order to solve the problem, I have used 2 equipments here. That means cost will be high, right? Now I am giving you another solution to the same system. Again I have a source, then I have a load, the nature of source is AC and the nature of load is DC. So I needed an inverter, right? AC to DC converter. Let me call it as inverter 1. Now what I am doing is, again, so since the power factor at this point of common coupling was low, so I wanted to improve the power factor. Now in order to improve the power factor, the another solution that I am giving to you is, instead of putting a separate shunt compensator, if I add a feature inside this inverter itself that will give me unity power factor, then what happened in this case, I am able to suffice my needs by using only one equipment instead of two. If instead of two I am just using one equipment, that means I have reduced the cost, right? And I am able to justify the cost of this inverter also, right? So this is what we'll be studying in this week's lecture. So what people started doing is, people started using the inverters or the already existing power converters which were already present in the grid, and people used them to improve the power quality instead of putting another compensator just for the sake of power quality improvement. They modified the algorithms, or they modified the inverter setup that was already present in the grid, right? So this is a much more this sounds like a much more practical solution to the problem. So therefore these kind of compensators have become very popular in today's era. So this is what we'll be discussing in today's session. So we'll be discussing about AC to DC converters, single phase, three phase, that are able to help with the power quality problems, along with solving the purpose of converting AC to DC. That too they will do. So they are initially, inverter in this first configuration was doing only one function. It was doing AC to DC conversion. But the equipment in this case is doing AC to DC conversion, and it is also doing power quality improvement. Okay, so this additional factor has improved the cost effectiveness of this equipment number 1, and therefore people have started using it much more. Okay, so we'll be discussing about these kind of AC to DC converters, single phase, three phase, multi phase, and after that we'll be discussing a little about solar energy conversion systems. And similarly in solar energy conversion system also the same principle we just saw. So initially we had solar power, right? So solar power gives output in DC, right? And our grid is present. A grid is AC in nature. So I needed an inverter, DC to AC, right? Now this inverter was needed. So this inverter initially was doing only the purpose of converting DC to AC. Now what I did is, instead of putting a power quality, improvement device in shunt, additionally, this will be number two, number one, additional equipment. What I did is, to the same system, in this inverter itself, I have added the feature of power quality improvement. So again, instead of two equipments, I just needed one equipment, and therefore my cost is justified. So even for solar energy conversion systems also, we will be seeing these kind of converters, which help us in power quality improvement. Okay, so this will be the discussion
Madam,
for
here,
today's.
madam,
Yes, sir.
here you are using in solar to DC, you are using shunt common system, madam. If it is not solar, directly it is battery. You no need to use any power quality improvement device, madam.
Yes, if it is battery, then you don't need. But solar is giving power in the form of DC, right? And it is variable in nature. So you need some kind of compensator here in order to take care of, in order to give a fixed kind of supply. So
Intermittent, because of intermittent nature only, you are putting a compensator, madam.
no, so
Power quality
compensator,
improvement.
power quality improvement. So for intermittency problems, so there are a lot of, we'll be discussing that in today's lecture. So when you talk about solar energy, there are a lot of types of solar energy conversion systems. Some have battery inside them, some are standalone, some are connected to grid, some are not connected to grid, only local loads. So depending on what kind of system you have, so it will depend on that. Okay, so mostly the compensator I am talking about is for power quality improvement itself. So you are right that if battery is there, then we won't need this power quality improvement device there. But with battery energy storage system also, then there are another kind of power quality equipments that come into picture. And then again, even with battery, so whenever solar comes into picture, we will discuss that in today's lecture only, that when solar comes into picture, you do the maximum power point tracking, right? So there is a controller and a converter involved there itself. So so that the nature of current that is coming from that is not very constant, and you need to take care of certain power quality problems specific to the field of solar. So this shunt compensator was serving that purpose here. Okay, so let us start our discussion for today. So in today's lecture, we'll be discussing about AC to DC converters that will that cause power quality problems. So as I discussed that the power electronics load that are present are also the cause of power quality problems. So we are using. So did you get the irony of it? That these power electronics equipments are drawing non-linear current, and therefore there is a need for power quality improvement. And this need of power quality improvement is solved also by power electronic equipment. So these AC to DC converters, they are solving the problem in a bigger picture. We have looked at the reason why these AC to DC converters have become popular were because they were helping us to improve the efficiency of the system. The reason why we moved from incandescent lamps to uh, LED bulbs is because LED bulbs were able to give us highly efficient system. A 5 watt A 5 watt LED bulb is able to give us the intensity equivalent to a 50 watt incandescent bulb. So definitely we will shift to LED lamps, right? But when we come to LED lamps, then there is another problem, that are certain power quality problems. So in order to solve that power quality problem also, we are using power electronic equipment only. Now, so we'll start with discussing which are the AC to DC converters that cause power quality problem first. First, we'll study which converters are causing these problem, and then we will start discussing about the solutions to that problem. And since a lot of content was covered in this past week, and we have a lot to cover. So I'll quickly browse. I'll just give you an overview of what these lectures were trying to communicate. So I cannot go into depth of all the lectures because we just have very little time in order to do that. But in case you have any specific doubt, then please feel free to stop me and ask. Okay, so let's get started. So a large number of loads use AC to DC converters as front-end converters. And the rating of these converters range from few watts to megawatts. And such converters can be classified based on the nature of AC supply that they want, based on the control of semiconductor devices that are using, and then circuit configuration which they are using. Depending on the type of filters used for filtering the rectified DC, their behavior vary in a number of ways. So there are output filters, right? We will see. So there could be simple L type of filter, or there could be simple C type of filter, or there could be LC type of filter. So lot of filters are possible. So with each variation in the type of output filter we are using, the nature of power quality problem and the current consumption varies from converter to converter. And these converters exhibit poor power factor at the AC mains, generally due to harmonics only, but with reactive power as well. So conventional AC to DC converters, that means conventional rectifiers, which are present in our electrical system, they inject harmonics and they have reactive power issues. So because of these problems, so these AC to DC rectifiers give rise to these power quality problems. So the key performance parameters for these rectifiers are, so whenever we talk about a rectifier, we derive voltage relationships for them. Voltage relationships means input output voltage relationships. We find the average, RMS and peak voltages. Then we find average, RMS and peak currents, and we try to find the current relationship between the input and output currents. Then we try to find the rectification ratio, form factor, ripple factor, distortion factor, displacement power factor, true power factor, transformer utilization factor. All these parameters we have already discussed and studied in our basic course on power electronics, and that these performance parameters are used for defining any kind of AC to DC converter. So if you look at the state of the art, then in today's world, a lot of solid state self-commutating devices have come into picture, like MOSFETs, IGBTs, GTOs. So these switches are being used in the latest converters. Then there are improved control approaches. So initially, the control algorithms were mostly analog in nature and hardware based, but nowadays, due to advancement in the field of DSPs, that is digital signal processors, and we are able to, we have reached a very high clock frequency. We have reached 200 megahertz clock frequency. Because of all these things, we are able to find out new control approaches which are very much better than the past conventional ones. Then there are a lot of hardware topologies available: full bridge, half bridge, full wave. Lot of options are there. So depending on that, we can make a change. Then there is revolution in the field of microelectronics. So initially, if you look at, this was IGBT switch, right? We all might have seen these kind of IGBT switches in our labs. So nowadays, in latest, what has happened is there are ICs, that is integrated circuits, which are coming in the market that have these switches inside them. So instead of putting a separate gate driver and this IGBT switch, I am able to put a simple IC on my board, and that IC has 8 switches inside it. Not just one, 8 switches inside it. I just have to give gate pulses to this IC, and this IC will work like a converter. Sorry, it has six switches inside it. So the IC which I am talking about is CPOS IC. This is from Infineon. So this IC is it looks like something like a miracle, right? Initially, when you have to turn on a switch, you have to design the gate driver circuit. Then gate driver circuit you give to PWM pulses. But all of that has just come in one simple small IC. It's a very small IC. It's a bit costly, but it's very small. So in that IC, there are 6 switches present. So you can make a 3-leg converter from one IC. You just have to give the PWM pulses to that IC, and it will do the switching. Okay, so this is the advantage of advancement in microelectronics. Then if you talk about the sensing devices, So you know that our eyes are the basic parameters that help us receive any kind of information. If I start getting blurriness in my eyes, then if I am not able to see things properly, I will definitely not be able to perform rest of the task very nicely, right? It will be difficult for me to read basic things. So if our similar in a similar way, if our sensors are not accurate, if our sensors are not able to measure high frequency noise, if I take a sensor in my system that has 50 kilohertz of bandwidth, and I am using that sensor in order to detect a noise which has bandwidth of 100 kilohertz, my sensor will not be able to detect it, right? It will show that there is no noise, but actually in that system there will be noise. So therefore you have to take care of all these things. So which sensor you choose for your application, that is a very important task that we normally neglect in many cases. So you have to take care of these things when you are doing a proper design. Then there are high speed and high accuracy microcontrollers and digital signal processors, right? As I mentioned that there is high accuracy, high speed, like the 200 megahertz clock frequency. If you increase the clock frequency, the speed increases. So that is why high speed and high accuracy. So all of us want maximum accuracy, right? None of us want that I want 10% error in my reading. Everybody, all of us wants, our output with 0% accuracy. Uh, but uh, the cost for high accuracy you have to pay. So when you want a high accuracy DSP, you will have to increase the cost of the system. So there again a trade-off comes. So what is how much of the error is tolerable in your system, and depending on that you decide which kind of DSP to use in your application. So if you look at the application of few of the AC to DC rectifiers, so there are switched mode power supplies in all of our labs, right? We all have visited the traditional electrical labs, and there are these power supplies which you set, there is a knob, and then you set the power supply rating to 15 volt, and then you connect your circuit. All these have AC to DC converters inside them. Our mobile chargers have AC to DC converters. Then our computer, if you open our CPU, then you will be able to see these kind of cards. This is our computer power supply card. This is an inductor. So if you have seen motor drives in your company or some other place, so these are drives. If you open the door, you will see a lot of PCBs are present inside this enclosure. So these are again, they all contain AC to DC converters. LED driver contains these converters. Electric vehicle battery charger contains the converters, and all the equipments that are used in still rolling mills, paper mills, printing presses, textile mills, traction systems. Traction systems means our railways, our metros, the home appliances that we have. Almost every around us, everything is electronic in nature, and they have a front-end pi electronic converter. So all those home appliances have AC/DC converters. And portable hand tool drives. So we use you all of you might have used a drilling machine in your life. So all that drilling machine has DC. We connect the DC battery inside those in order to make them handheld tools. So you just connect the DC battery, and then they have a DC to AC converter inside them. Then there is high voltage DC transmission. So while doing high voltage DC transmission, what you do is you have AC that is at the generating station, right? Because motors, when just generators that they generate AC electricity. Now, my loads in general are also AC in nature. Now, the reason I go to DC, why do I prefer DC transmission? Why not just if you talk about AC, you have to put a lot of transformer. Then you have to there is inductance and capacitance in AC, so you have to put some compensating statcom in between or something. Then it's very bulky system. On the contrary, if you have to transfer the same same amount of electrical power over longer distances, what you could do is you could use a AC to DC converter here, and then you could use a DC to AC converter here. And since in DC, there is no significance of a capacitor or an inductor, all that problems go away. And if you want to transmit electrical energy over very long distances, so HVDC has high voltage DC transmission has become very popular in today's era. So therefore, this is the another way of doing. electrical power transmission. So in this transmission also, there we are in this high voltage DC transmission also we are using AC to DC and DC to AC converters. So again, there are all these equipments have in AC to DC converters used inside them. Now, if you talk about there are home inverters, welding machines. This PCB is present inside your ceiling fan. Sometimes, if your ceiling fan goes bad, just try to open it. You will see a PCB something like that. Okay, so these are all the examples of AC to DC converters around us. So if you try to classify these AC to DC converters, then the broadest category will be in the basis of single phase and three phase. Now in single now in this subcategories, you can have uncontrolled, semi-controlled, and fully controlled. Now I hope you know what these means. So when you talk about uncontrolled, there is no control as the name suggests, and as there is no control, these converters are made up of purely diodes. And in semi-controlled, they are made up of combination of both switches and diodes, because some switches are controlled and some are uncontrolled, since the converter name is semi-controlled. And in fully controlled, all the switches are there. There is no diode. That means all are controllable. So these categories, then the subcategories have lot of possible topologies. It would either be half wave, full wave, bridge type, voltage doubler. Similar to these, all categories are present inside all of them. Then when you go to three phase or higher phases, then there in three phase there is another category, that is multipulse converter. Then multipulse converters could be isolated or non-isolated. And then in fully controlled, there are another variation, that is dual. So what is the meaning of dual is, if suppose I have a motor and I want to, if I have this motor, I have this converter, and I am able to rotate it in clockwise direction using this converter. Then what I can do is, if I want to make an anti-clockwise rotation also, I can connect two such converters in anti-parallel. So this will be called this is converter 1, this is converter 2. So now motor, if I turn on converter 1, it will rotate in clockwise direction. If I turn on converter 2, it will rotate in anti-clockwise direction. Therefore, using both this converter 1 and 2, I am able to rotate the motor in multiple directions. Okay, so that is what a dual converter means. So you use multiple converters to obtain 4-quadrant operation. So when you try to rotate motor in all in both the directions, you call that the motor is operating in a 4-quadrant mode. Right? So if you want, if these 2 quadrants are given by converter 1, these 2 quadrants will be given by converter 2. So this is how you are able to achieve 4-quadrant operation. Okay. So if you look at the topology one by one, we'll quickly have a glance through these topologies. So if you look at the single phase AC to DC converter, uncontrolled one, so we know that since it's uncontrolled, it will just have a diode. So this is a half wave configuration. In half wave configuration with uncontrolled, there will be just one diode. If you want to use with an L filter, there will be one inductor. If you want to use with a C filter, there will be one capacitor. If you want to use with a LC filter, you will have this kind of configuration. So similar analysis will be done for lot of converters. So this was half wave. Then we'll go to full wave. So this circuit is of a full wave. So there are 2 diodes, and then load is connected between these 2 terminals. Sort of a midpoint rectifier. We have seen these midpoint transformers, right? So this is sort of a midpoint rectifier sort of topology. So these are called full wave configuration. Then again, here the load is connected without any kind of filter. Here the load is connected with L type of filter. Here the load is connected with C type of filter. Here the load is connected with LC type of filter. So all these 4 variants will be available for all the types of topologies. Then this is full bridge. This is an H bridge or full bridge. They both are the same thing. So this bridge type of configuration is called the full bridge configuration. Then this full bridge configuration can be without any filter, with L type of filter, or C type of filter, or LC type of filter, right? Then this is the same voltage doubler configuration. This circuit is used for doubling the voltage. If at input you have 115 volts, then you could get 230 volts at the output using this converter. So this voltage doubler circuit, again without any filter, with L type of filter, with C type of filter, and with LC type of filter. Then these are semi-controlled. So in semi-controlled, if you look at half wave, there is one switch present and then there is one diode. So therefore these are called semi-controlled. And then again they are having categories in which there is load without any filter, load with L type of filter, load with C type of filter, load with LC type of filter. Then again full wave configuration with semi-controlled. So there are two switches and one diode, hence semi-controlled. Then there is bridge configuration in which there are
Madam,
four
the diode
switches
is freewheeling diode,
and
madam.
one.
Freewheeling
Sorry?
diode. The diode is freewheeling diode, madam.
Yes. So this is a full bridge configuration. This is again semi-controlled. Now if you look at fully controlled converter, then there will be only switches in the fully controlled converter. So these are half wave fully controlled converter. Then this is full wave ones. Again, two switches, no diode. Then these are bridges, all switches, no diode, right? So then there is these are dual converters. So if you look at these dual converters, one half bridge, this is one side of the one half bridge one, and this is another half bridge two. This is half bridge one, this is half bridge two, and load is connected in between. So this dual converter is helping us to take current in both directions through the load, right? Therefore it is called dual converter. So again, in this full wave dual converter, there is one full wave converter on the left and another full wave converter on the right. So hence again dual converter. Then this is bridge type of dual converter, one bridge on the left, one bridge on the right. So any kind of converter can have its dual. Okay, when two such converters are used, it's called dual configuration. Now we have looked that there are L type of, C type of and LC type of filters. Now let us discuss something about filters. Filters are commonly employed in rectifier circuits for smoothing out the DC output of the load. So when you talk about DC, ideally whenever somebody asks you to draw a DC waveform, you just draw a very light straight line, right? But in reality, there is no such pure DC existing, because whenever there is DC, that DC is generated using some kind of conversion. So when you use DC for converting, the output that comes is something like this in nature. That means it is not a fixed pure DC. It is a DC with some amount of ripples present in it. So therefore, due to the presence of these ripples, it is never a pure DC. So in order to reduce the nature of these ripples and make it close to a pure DC, we put filters there. That is the purpose of putting a filter. Okay. So smoothing out the DC output voltage. So if I smooth out the DC output voltage using a filter, then my ripple wala DC will look something like this DC. Okay, so therefore I am using filters. Then filters are classified into inductor input DC filters, capacitor input DC filter, and then inductor input DC filters are preferred in high power applications, whereas capacitor input DC filters are used mostly in low power applications. So this is the application areas of these filters. So filtering action A is more effective in heavy load conditions than in light load conditions. If the ripple attenuation is not sufficient, even with large values of inductance, an L section filter can be used for further filtering. So if I want a simple smooth output, I could just go with the L filter. If this L filter is not able to take care of the crests that are, or the peaky current that is coming, then I can add an additional capacitor filter, this peaky output with high crest factor. Okay, then basically depending on, so when you have an inductive filter, your voltage is not exactly like this is the average variation of the voltage. So actual variation of voltage is something like this. This is the actual waveform. So this is close to a square wave, but it is not actually a square wave. So these ripples, so if you look at the pure DC something looks like this. Okay, this happens due to the presence of inductive filter. If you put just a capacitive filter, then the nature of output voltage would be something like this. Therefore, a lot of times you use both combination of L and C type of filter. Now, if you look at the analysis of these kind of filters, so whenever you want to do analysis of any kind of AC or DC filter, what you do is you look at here it's just one diode, right? There is no switch, so there is no gating pulse. So you can just draw the waveform of input supply voltage, and then you know that this is a waveform of input supply voltage. Now you know that diode will conduct only during the positive half pulses. That means this V naught will be this. Sorry, V naught will be actually this. It will be 0 during the negative half cycle. So this will be my V naught. And I know that I naught is equals to V naught by R. So this red waveform that is present here is, so the red waveform that is present here is I naught, right? This is easily obtainable, right? So you just have to look at the circuit. You need to draw the input voltage waveform. Then you need to draw a timing diagram based on the behavior of this device that is put. So since it was a diode, we didn't have to think much. But if this is any other device, then we have to take care of what is the behavior of this device in present, in positive half cycle and in negative half cycle. And from that we can draw the waveforms. And from waveforms we have learned to find out the average value, then the RMS value. Then we can use the waveforms for doing Fourier analysis, and from that we can calculate the harmonic components of these voltages, right? So these are few examples of how to do the analysis of any kind of AC to DC converter. Then sir talked about few numerical examples, and the basic principles involved in all these numerical examples we have already discussed. The standard definition of ripple factor, all these things, these are just formulas. So I don't feel any need of discussing them. And then there are comparison tables present. So in case you want to choose between which topology to use and what are the differences in all the topologies, you can look at this comparison table. Okay, so the main factor that we look at is THD. So you can compare the THD. So depending on application, what your application needs, whether I need the rating of my converter to be less in order to save cost, or do I need to have a higher rectification ratio, or I need to have a lower ripple factor. All these things, whichever is your basis of decision, you pick them, and based on that you make a decision. Then let us talk about three-phase conventional AC to DC converters. We talked about single phase so far, right? So if you talk about three-phase, so half wave, if you talk about, this is the half wave configuration for three-phase circuits. So in this circuit, this is the uncontrolled version. Therefore, only diodes are present. If you look at the full wave will look something like this. If you look at the bridge configuration will look something like this. And all these configurations are present with L type of filter, C type of filter, and LC type of filter. Then there is configuration of three-phase uncontrolled 12 pulse non-isolated AC-DC converters. So now the number of pulses they are trying to increase. What will be the advantage of increasing the number of pulses? By increasing the number of pulses, the ripple reduces. So if you look at this diagram here, then if suppose this is my total time period T, then if in one time period I have 3 pulses, then my, let me say, pure DC is like this. And in same, if I have 6 pulses now, then the this ripple content, this is my ripple content compared to this ripple content. So if this is like, this is x1 and this is x2, then x2 is less than x1, the ripple content reduces. So this is a 3 pulse DC output and this is a 6 pulse DC output. Therefore, by increasing number of pulses, you can reduce the ripple percentage, and therefore we go to higher pulse converter. But the other side to this part is that when you go to 6 pulse converter, you know that you are increasing the number of switches, increasing switches. And when you increase the switch, you increase the gate driver circuits, you increase the PWM pulses, you increase the protection circuit, and then what goes up? Cost goes up. So if you want a cheaper cost, then you can compromise with the ripple in the DC output. If you want a very pure, beautiful DC, then you have to increase the number of switches and then you have to increase the cost. Therefore, you can have power supplies available in market from 30,000 to lakhs. So there are power supplies which are available in 2 lakhs, 3 lakhs. And there are power supplies which are available for few thousands. So the parameter that is varying in amongst these amongst these power supplies is their accuracy or the ripple content. So the costlier one are pure DC, pure closer to the pure DC, and the far away ones or the cheaper ones are have lot of ripple inside them. So depending on your application, if I am using a medical equipment, then I don't want any kind of spikes in my medical equipment to manipulate the readings of my patient. So therefore, in medical equipments, I will use a very steady and pure form of DC supply, and that is the reason medical equipments are very costly. Because there is you cannot say that electricity went and the readings are not there with you. You have to connect a UPS or a uninterruptible power supply backup for every critical equipment. Then you have to put a pure DC power supply so that there is no noise in the output result. If your ECG has some erroneous output result, and because of that you are given certain prescription, that will be very erroneous, right? So you don't want that. So therefore, you use the best quality of power supply for medical equipments with power backup. And therefore, the cost, if you look at the cost overall of these medical equipment, it is very high. It is in crores. Most of the medical equipments are very costly because of the same reason. Each of them have their individual power backups. Each of them will have their individual memories and highly accurate power supplies. So these are the factors that you need to take care. Okay, so there is always a trade-off in engineering. So then you look at the configurations of the three-phase uncontrolled 12 pulse. There are isolated configurations available, non-isolated available. So the basic principle is always the same. You are converting AC to DC, and then here in order to obtain DC with lesser ripples, you're trying to increase the number of pulses. Then few examples were solved from this area as well. Yes. Then we came on to the topic of improved power quality converters. Now, so far we have been discussing about the AC to DC converters that cause power quality problems. That means the AC to DC converters that are present around us and they are causing power quality problems. Those converters we studied so far. Now there are few topologies, as I mentioned, that nowadays people have started adding this feature of power quality improvement within these AC to DC converters, and these AC to DC converters with the feature of power quality improvement inside them are called as improved power quality converters, IPQC. So there are IPQCs, that means within the category of improved power quality converters, there are a lot of converters that come into picture. AC to DC boost converter, AC to DC buck converter, AC to DC buck boost converters. Lot of varieties are available, and we'll be just going through a brief description about these topologies. So if you look at these improved power quality converters, let us start with discussions about AC to DC boost converters. So the AC-DC converters that we have discussed, they have the demerits of poor power quality in terms of they are injecting current harmonics into the grid, they cause voltage distortion, they have poor power factor at input, AC means, they are slow, they have rippled DC output, the efficiency is low, the size of the AC and DC filters is large. And the solution to all these problems is, in order to take care of all these power quality problems that are present inside the AC DC converters, we are replacing these AC to DC converters with improved quality power converters, or they are also called switched mode rectifiers. So that is the solution to these problems. And as a state of the art, these in improved power quality converters technology has matured for AC to DC conversion with these power quality improvements. So they are able to reduce harmonics, they are able to increase the power factor, they are able to take care of electromagnetic interference. They are able to output well regulated, good quality DC output, and the rating is ranging from the ratings that are available ranges from very few watts to several hundred kilowatts. And the classification of these IPQC converters are available they are available in both unidirectional and bidirectional power flow. So power flow direction, I hope you understand. So if there is source and there is load and there is a network, so if this network is able to transfer power only from source to load, it will be called as unidirectional power flow, right? Because only power is able to transform from source side to the load side. On the contrary, if I am able to transfer the power from source to load and from load to source in both directions, then it will be called as bidirectional. Because nowadays we have solar, right? And solar, sometimes using solar, we pump the solar energy into the source, right? Into the grid, we connect it. So that means we need converters which have the capability of bidirectional power flow. So depending on application, we select whether we want to go for a unidirectional power flow or a bidirectional power flow. Okay. So they apart from this variation of unidirectional and bidirectional, the other classification categories are boost, buck boost, multi-level converters, single phase and three phase. Okay. So another category of IPQC for high voltage and high power applications is multi-level and multi-pulse converters. Okay. So if you look at the classification of IPQC, it can be based on the topology. It could be boost, buck boost, multi-level, unidirectional and bidirectional, current and power flow. Then it could be on the basis of converter, whether it could be a voltage source converter, current source converter, step up chopper, step down chopper, etc. Then the third classification could be on the basis of the phase supply. It could be a single phase supply or a three phase supply system. Then other classification is on the basis of structure. It could be on the basis of the structure, that is, it could be a bridge, it could be a semi-bridgeless, it could be a fully bridgeless topology, depending on the application. Or and if you try to classify it on the basis of design and control, then it could be a continuous conduction mode based, or it could be discontinuous conduction mode based, or it could be critical conduction mode based. What is critical conduction mode? So when you transition from continuous conduction mode to discontinuous conduction mode, there is a boundary condition. So below that boundary there is continuous conduction mode. After that boundary there is discontinuous conduction mode. So this boundary is called critical conduction mode. Okay. Then if you look at the control of IPQC, then there are a lot of algorithms that are available for control of the current. So the algorithm could be, one algorithm example is peak current control. Another one is average current control. Then it could be a hysteresis control. So these are just examples. Then another one is borderline control. So in these lectures, only few of the control algorithms are discussed, and that too in not that much depth. So if you need any additional details about these algorithms, you'll have to refer certain kind of websites or reference material. But apart from these control algorithms, there are a lot of control algorithms which are actually available in the literature. Okay, so you can understand these algorithms in order to understand. So sir has discussed a few of the most popularly used algorithms in this area, and then by keeping them as basis, you will be easily able to understand any algorithm that you will ever see, you will ever come across. Then there is discontinuous current control algorithm. Then we talked about supply system based classification. It could be done on the basis of single phase or three phase. And then they have the category of unidirectional or bidirectional, right? Then if you talk about the classification of single phase IPQC, then single phase IPQC again has classification of unidirectional or bidirectional. Then this unidirectional will have boost, buck boost and multi-level. Then these four classifications will again be present in bidirectional. So bidirectional is when do you need bidirectional? Our online UPS. UPS is uninterruptible power supplies. So sometimes at our home we have battery. We have inverters in our homes, right? So what does these inverters do? So what happens is when we have the power in our homes, then these inverters charge the battery, and when the power goes, then these inverters convert the DC power present in these battery into AC power, and using that AC power we are able to illuminate the loads present in our houses or provide electrical energy to our houses. So that is what that is what happens when we talk about uh, UPS, online UPS. So in this UPS, you are doing both. You are doing power transfer in all the directions. You are doing power transfer from the battery to the home and also from the home to the battery. That means you need bidirectional power flow capability. Therefore, bidirectional type of converters are used in online UPSs. Another example of unidirectional UPS is ACs, our air conditioners, refrigerators, washing machines, welding machines. All of them have, they are all, most of the converters that we have in our houses are unidirectional in nature because we only need to give power to these devices. We don't need power back from these devices, right? So therefore, they are called unidirectional converters. Then if you look in the category of single phase unidirectional boost IPQC, then this will be a basically what is happening here is this is a boost converter. The this red circle thing is a boost converter. So first, what we do is boost converter is a DC to DC converter, right? Where the output voltage is higher than the input voltage. That is the property of a boost converter. So what happens in a boost converter is you use a diode bridge rectifier in order to obtain the DC at this point. Then you using the boost converter, you convert this DC into another form of DC which is higher than the input voltage, and then you apply that across the load. Now, this is called a single phase unidirectional boost IPQC. Then this is a symmetrical two device. This is another topology serving the same purpose. So lot of topologies are possible. So this is then again another topology, then another topology. So all of these topologies have their own advantages and disadvantages. So depending on what your application is and what do you want in your particular case, depending on that you should decide which kind of topology do you want to go with. And in order to do the analysis of these circuits, you can do it in the form using the waveforms as we have discussed previously, or you can write mathematical equations. The mathematical equations might, the end equation might look very complex, but always start from the basic. How to start with the basic? If suppose I have this circuit, I know that I know the gating pulse that I'll be giving to these switches. So first I will name it as switch 1, switch 2. Then I will see in which duration switch number 1 is on. Then in that duration I will draw an equivalent circuit for this circuit during the time when the switch 1 is on. Then I will write the KVL and KCL. The basic equations are always same. The combined equations may look very bulky, but they are all derived from using the basic electrical principles. So just apply KVL and KCL, and then you will be able to easily obtain, you will be able to understand the circuit better. And then what you will do is you will do the similar analysis when the switch number 2 is on and switch number 1 is off. So in that circuit, in that particular case, you will again derive the equivalent circuit, and then from that equivalent circuit, you will write the KVL and KCL equations in order to obtain the expressions. Okay. So this similar procedure when you use, you will be able to understand these equations, and in case you have any doubts, you can always refer additional reference materials. Okay. So then this is again bidirectional boost IPQC for bidirectional power conversion. Then this is half bridge based, this is full bridge based. So after don't get confused by you reading all these topologies. The basic principle behind all these topologies just tells you that there are a lot of topologies available, and another thing that they tell you is that you could analyze any random circuit given to you using the same basic principle. So just use these multiple topologies to do the analysis. You can use any form
And
of
major
textbook.
difference between madam, major difference between the conventional converters and buck boost converters, that SCR switches replaced by IGBT switches, madam.
No, in any form of converters, you can use all SCRs or IGBTs or buck boost or MOSFETs. So nature of switches does not define the type of converter. The type of converter could be anything. The basic thing in these converters is that they are boost converter. What does a boost converter do? A boost converter converts input voltage to a higher output voltage. And if this circuit is doing that, it is just a black box. If I give you a black box that is able to convert input voltage into some other output voltage, such that output voltage is greater than input voltage, and the nature of both input and output voltage are DC in nature, then it is called a boost converter. This is only the thing that you need to understand. Rest in this dabba, any switch you can depict the topology using any kind of switch. This switch that I am depicting here could be a MOSFET, SCR, IGBT, anything. So since in today's world people have started using mostly MOSFET and IGBTs, therefore they have replaced them with IGBTs. Otherwise, there is no difference. The type of switches
So
does
here
not.
using a two circuits, madam. Rectifier, one is a rectifier circuit up to V in DC, and then I have to use one more
Yes, this is a
converter,
two-stage
madam. So
conversion. Yes, because since boost converter is a DC to DC converter, right? So you cannot connect AC input to a DC. You cannot connect AC input here, right? You'll have to convert it into DC, na? So since the input to a boost converter is DC in nature, therefore first you will convert the available AC using a diode bridge rectifier to DC. And why did we use diode bridge rectifier? Because it is the cheapest again. You could use a control rectifier also, but it will necessarily increase the cost. You anyways have the boost converter to control the output voltage. That is sufficient for us.
here in this circuit, madam, only capacitor only act as a boost converter, madam. Means here it is available DC output of the circuit.
No, so if
It-
you look at the working
it-
of this particular circuit, then what will happen is if when you are turning this switch on, okay, let me say when you are turning this switch on, then this inductor will charge, right? And this diode is there, so this inductor will charge. And when I am opening this switch, then this inductor will give its energy to the capacitor. So that means the boost operation is happening, right? So this is the inductor and the capacitor that are involved in the boost circuit.
Okay, here the capacitor not act as a filter, madam.
There also the
Filter also,
capacitor,
madam.
even in the standard boost topology, the capacitor is acting as a filter only.
Storage also.
Filter,
Storing.
not storage exactly, filter. So the reason of putting a capacitor cannot is not a battery, right? It cannot store. It can help you maintain the voltage to a level for certain duration of time.
Yeah.
Okay, so in these applications, you will have to look at the switching pulses to these switches. So the basic principle why a boost converter is called a boost converter, because boost converter in one switching cycle it will store all the energy inside the inductor. Then in next switching cycle it will give all the energy in the inductor and the source both to the load. So here the same thing
Madam,
is
same
happening.
topology also available in conventional converter, madam. This is same topology also. This is switches, filter, like the same topology also in conventional converter. There in that, what is the major difference, madam?
The switching, the gate pulses that we are giving are different, right? There we are giving different gate pulses. Here we are giving different gate pulses. Since these are, see, in power electronics, in most of the active circuits, the topologies will look same to you, but they are just the half part. These topologies, what will be the final output voltage VDC will depend on what switching sequence is being applied to these switches. That defines the whole purpose. I can use this standard edge bridge converter to generate AC voltage also. I can use this standard edge bridge to generate DC voltage also. It depends in what way I am using it. Okay, so the switching pulses determine these. These are only the hardware topologies that are shown here.
Like this is a voltage source inverter, madam. This is a voltage source inverter. This one.
Yeah.
Okay, okay. In that conventional, not voltage source inverter, madam. Just you are using bridge, just you are using SCS or like that. No,
Sir,
no, like
this
that,
is
madam.
also called a full bridge only, because full bridge means this arrangement of switches. Now, this is the physical arrangement of switches. Now, after connecting the switches in this physical manner, physical arrangement of switches will remain the same. But if I am calling these switches as switch number 1, 2, 3 and 4. But if I am turning on switch number 1 and 4 at one time and 2 and 3 at the other time, this will give me a rectified output, full wave rectified output. And if I want a boost operation, then I told you, different switching sequence. So by connecting the same physically connected switches in different manner, I can obtain different output waveforms. The same physical arrangement means full bridge. This is a full bridge, physical arrangement is same. But in order to give it boost operation, I'll have to take care of the switching pulses.
How will get more than source voltage, madam, in that boost?
That is the basic principle of boost converter, right? In a boost converter, the output voltage is equals to input voltage by 1 minus duty cycle. So if you put any value of duty cycle, you will get the voltage more than the input voltage. That is the basic principle of boost converter. Na?
Okay, okay.
Okay, so you what you do is you put the gating pulses, and then based on that gating pulses, you get your D. Then from using that D, you obtain the relation between input and output voltage. And when you look at the relation between, like for the buck converter, V naught is equals to D time Vn. That means since duty cycle lies between 0 to 1, V naught will always lie between 0 to Vn. That means V naught is always less than Vn. That is the characteristics of a buck converter. Similarly, this is the characteristics of a boost converter. So whenever you just have to do the similar KVL KCL analysis and then obtain the input output relationship of the voltage and the current, and from that you will be able to obtain what kind of circuit this is. And since it is doing the boost operation, therefore it is called boost converter. The physical arrangement alone is not making this converter boost. The physical arrangement along with the switching pulses is making this converter a boost converter. If you still have doubts, you can check out, you can try giving different pulses to this particular switching arrangement, and then you will see that you are getting different outputs every time you are giving a different gating pulse. Okay. So then similarly, a lot of topologies for boost converters are given, and then they are analyzed. Then they have given boost these AC to DC converter topologies with isolation. So when you talk about isolation in these circuits, they are high frequency transformer isolation. Why high frequency? Because with increase in frequency, the size of transformer reduces, and when size of transformer reduces, it reduces the space, and it's a better form factor also. So therefore we provide high frequency transformer isolation. And another reason for needing isolation is the safety of the consumer. So whenever there are certain applications in which there might be danger to the life of the consumer who is using the equipment, then we have to take care of these parameters. Okay, isolation or non-isolation. But definitely, since we are adding an additional component, and it will be definitely increase the cost of the system, therefore isolated converters are in general more costly than non-isolated ones. Then if you look at the classification of these transformer isolation based converters, then they are again categorized into buck boost and buck boost. And then based on the buck derived, there are forward converter, push pull converter, half bridge converter, and bridge converter. And again, these categories is present in boost also. And for buck boost, there is flyback, Cook converter, CPIC converter, zeta converter. So these are only again the very few converters that are discussed here. A lot of topologies are available, and the only thing you need to learn from these lectures is that how to analyze them, and the standard procedure will remain same almost for all the circuits. So you can practice from the lectures. These are again the few topologies with their control algorithms for isolation, and these are few applications of these AC to DC converters where boost converters are present. So DC power supplies, telecommunication power supply, improved power factor ballast. So power supply equipment for computers, medical equipments, printers, scanners, etc. Then drive application for power factor improvement at AC side, electrical welding, lighting such as CFLs, all these have boost converters inside them. Then the first configuration that we studied was one with diode bridge, right? We needed a diode bridge at the start in order to convert the AC available into the DC. Then this configuration is called power factor correction using a bridgeless boost converter. And it's called bridgeless because in this particular configuration diode bridge is removed. Therefore it is called bridgeless. And it is called power factor corrected because this topology helps us obtain unity power factor. So this converter is giving us the boost operation along with power factor correction. Therefore, it comes in the category of IPQC, that is improved power quality converter. So there are again lot of topologies available. So this is one topology. This is another topology available. So a lot of topologies are presented in the lectures, and the same equations are used for deriving these, solving these numericals that are present in the lectures. You can practice them, you can simulate them, then you will get a better. And the most important thing to do is try to analyze them and derive these design equations. So if you do the same analysis for most of the converters, then you will be able to understand these systems better. Okay, then similar analysis was given for, so far we discussed IPQC AC to DC boost converters. Now the same analysis was given for IPQC AC to DC buck converters. So in the buck converter category, we know that they step down the voltage. So there are advantages of buck IPQCs. The voltage across the main switch of the buck converter is almost clamped to the input voltage. Therefore, the buck PFC converter can achieve relatively high efficiency since the number of devices are only one, so low device count is there, output current is continuous. These are the advantages. And if you talk about the disadvantages of buck IPQC, buck PFC converter fails to provide a sinusoidal waveform for the input current. The input current is discontinuous in nature. And there is a strong trade-off between power factor and the output voltage selection. So maybe the range of output voltage will reduce if you try to keep the power factor to unity. And the input current THD and the output voltage ripple is higher because of the discontinued current conduction. And the size of the smoothing inductor that is present in buck converter is also comparatively large. And application of IPQC buck converters are in lighting systems, battery chargers, DC power supplies, UPS, computer power supply, ceiling fan drivers, portable hand tools, home appliances, etc. So these are electronic ballast. So electronic ballast is present in our tube lights. So initially we used to have the choke coil, right? Some cuboid type of box was there. So whenever our tube light used to go bad, we used to check that choke first. That was mechanical ballast. That mechanical ballast is now replaced with an electronic ballast. Then there are LED bulb drivers. These all are IPQC buck converters. Then in mobile chargers, low power battery chargers, laptop chargers, computer power supply, ceiling fan driver, then fax machine supply, printer power supply. In all these places, IPQC buck converters are present. Then let us look at the classification of buck converters. So again, buck converters can be classified on the basis of supply. So this on the basis of supply, we could classify them into single phase and three phase categories. So these classification can be given in the form of both unidirectional and bidirectional. Similarly, we could do the classification on the basis of structure. So on the basis of structure, I could classify them as isolated and non-isolated first of all, then as bridge, semi-bridgeless and full bridgeless. Then I can classify them on the basis of design and control based. So on the basis of design and control method, I could use buck IPQCs with CCM control, by IPQC with DCM, continuous control, discontinuous control and critical conduction mode. Okay, so these are the three conduction modes. Again, we had discussed the similar for boost converter. And again, there are a lot of topologies available with different type of filters. So these are bridged configurations. Then again, bridgeless configurations will come for these, and then you will do the same analysis for these converters as well. The control algorithms used are almost identical for all the converters. The only difference is in the topology and the switching action. This is the PFC bridgeless PFC buck converter. So here in this topology, bridge was present, In this topology, the bridge is absent. Okay, so so now in this topology, we don't need a separate bridge. Then these are another topologies possible for bridgeless configuration. This is another bridgeless configuration. Then this is transformer isolated configuration. Then this is transformer isolation based on push-pull converter. Transformer isolation based on half bridge converter. Transformer isolation based on full bridge converter. So don't get overwhelmed with these things. These are just a few comparison tables. The basic gist that is involved in all these circuits is to understand that there are a lot of circuits possible, and the only thing you cannot learn the analysis of all these converters. The thing that you could actually do is try to understand the design process, try to understand the general method of analysis. If you are able to do that, then you will be able to do the analysis of any kind of converter. Okay, you won't have to remember the equation of any particular kind of converter. Okay, so again, we discussed boost converter at the first, then we discussed buck converters, and then we are discussing the buck boost converters. So this for the buck boost converters. Again, the applications of buck boost converters are electric vehicle battery chargers, electric drive systems, then our LED bulb, street light, uh, LED tube, luminaries, floodlight, home inverters, uninterruptible power supplies, then telecom power supply, computer power supply, welding machine, all these are buck boost converters. Another applications are wireless power transfer, electric aircraft, traction systems, home appliances like air conditioners, LCD display, washing machines, etc. and high voltage DC transmission system. So these are few other examples of buck boost IPQCs. Then if you look at the classification, again on the basis of single phase and three phase, they are categorized into unidirectional and bidirectional. Then on the basis of structure, they are categorized into non-isolated and isolated. And then in this category, they are categorized into bridge, semi-bridge and fully bridge configurations. Then another basis for classification is on the basis of topology. So the topology could be conventional buck boost converter, Cuck derived buck boost converter, Sapik derived buck boost converter, Zeta derived buck boost converter, or current switched converter derived buck boost converter. Then the classification another could be on the basis of control. So it could be continuous conduction mode control, discontinuous conduction mode control, or critical conduction mode control. These are again standard topologies. So CSC is cascaded control, cascaded converter. So in cascaded, there is a bridge that will convert the AC to DC first. Then there is this buck. Then there is this boost converter. This is called cascaded converter. That you literally just you are cascading the buck circuit with the boost circuit, and it will be the same this circuit. Then from this circuit we started reducing in order to reduce the number of components that are present. And then this is the with the bridge, because our diode rectifier bridge is present. Then we'll move on to the bridgeless topology, and then we'll move on to bidirectional topology. And then again there is continuous current mode conduction, discontinuous current mode conduction, and critical current mode conduction. Then there is again high frequency transformer isolations present. This could be on the basis of half bridge, full bridge, Sepik, Zeta. These are all the name of the different types of converter topologies. So whenever a converter topology becomes quite popular, then they start giving it names. So these are just the names of few of these topologies. So the same identical procedure is used for analyzing just simple KVL and KCL equations. You should definitely try to do these procedures so that it will help you understanding things better. And also you can simulate these things in MATLAB. So when you simulate in MATLAB, you will get waveforms like this. You will be easily able to understand the working of these converters, whether they are able to serve the purpose properly or not. Then these are another topologies for the buck boost converter. These are bridgeless topologies. Bridgeless means less number of converters. Then bridgeless buck boost converters with isolation. So we have discussed, right, why isolation is required. So the four main applications of isolated converters are as we discussed in medical equipments, high voltage circuits for the protection of the consumers, then in IGBT controllers and in power metering systems. So whenever we are metering the power could be very high. Basically anywhere where there is danger or there is criticality. In those areas we use isolated converters. Okay, so these are the examples of all these four particular categories. So, as an emerging application in welding recently, I don't know if I showed you the photo or not. Initially, if you look at the welding machines that were used previously, welding machines were so big in size that if I wanted to do welding at first floor or second floor of a building, it was not possible because that machine was so bulky. I could not take it to the second floor or first floor of the building. But now those similar welding machines are, this very small sized. They are portable. You could easily take these welding machines on any floor you want, and you could easily do the welding there. So all these, developments have come because of high frequency transformers. As I mentioned, these high frequency transformers are initially they were bulky because these transformers were very bulky. But when they reduce the frequency of these transformers and with all the advancements in the electronics technology, so the size of these transformers has reduced to very small, and therefore the overall equipment size has reduced, and therefore we are easily able to carry them anywhere we want. So this small transformers are present almost in all the equipments, and they are very cost effective also, especially for bulk production. So again, these are examples of isolated converters. Fly back, forward. You should definitely do the analysis of isolated converters as well, because most of the converters that are used in practice are isolated ones. Buck boost ones are mostly used for our study purpose only. Then in a similar way, we were discussing single phase IPQC or improved power quality converters so far, right? Now we'll move on to the category of three phase IPQC converters. So in three phase IPQC converters, there is solar energy conversion system and wind energy conversion system. So these are used in these conversion systems have the application of three phase converters inside them. So since a lot of big solar fields and wind parks are available, so what happens is when there's a big solar field, and then we want to collect the DC that is generated in this field, and then we take it to a central inverter. We connect all that DC into the AC, and then we pump it into the grid. So since we have a lot of since this is a very all these solar power fields, they are of acres and acres land. Therefore the power that they will be generating will be very high, and when high power is involved, then we increase the number of phases. In our houses we have single phase solar energy conversion system, but in solar fields we need to increase the number of phases because high power has to be transmitted to the grid, and grid in all these areas is mostly available in three phase forms only. We could connect the single phase to that three phase also, but the more efficient one will be connecting a three phase connecting it directly to the three phase AC supply, because we have a very high amount of power to transmit, right? So therefore we increase the number of phases, and therefore these high solar fields and wind energy farms, all these have three phase converters. They use three phase converters. If on the right you look at this AC microgrid and DC microgrid, then you can see that there are microgrid means small grid which is independent of our electricity grid. So if suppose I am in a village, and in that village I have a solar field. So using that solar field I will obtain my okay, let me say this is a wind field. So the wind field is generating AC supply. This AC supply I will create AC buses, and through that AC buses I will connect it to different kinds of loads which is present. This is an example of AC microgrid. Then I could have a solar field somewhere. Then I could connect it to a DC bus. So this is my solar array which is feeding to this DC bus, and then this DC bus is connected to all these loads which are present here. This is the battery storage. These are the houses which are getting the power. And if there is surplus power, if my solar field is able to generate more than what the local people need, then I can give that power to the electrical grid back. Okay, so these are again three-phase converters. Then three-phase converters are used in traction systems, cold storage plants, HVDC system. Again, there is high power transmitted. So these are again three-phase converters. Then there are electric vehicle charging stations. So all these electrical vehicle charging stations have three-phase converters. Then another applications are cement industries, mining and mineral industries, metal industries, marine and chemical industries, oil and gas industries, water industries, etc. So if you look at the classification of IPQCs for three phase, they're again categorized into unidirectional and bidirectional converters. And then these unidirectional converters are categorized into boost, buck boost, multi-level, multi-pulse, all these converters. Okay. So this again the categorization of these three-phase IPQC converters. Then again there is three-phase unidirectional boost IPQC. Then there will be three-phase bidirectional boost IPQC. Then there could be three-phase unidirectional buck IPQC. All these topologies are given in the lectures, and few of the popular ones like VNR rectifier. So we were discussing flyback, right? Flyback, forward. So similarly, these few other topologies are also discussed in detail in the lectures. And there is some delta switch rectifier. These are few popular ones that sir has picked up. Apart from that, lot of topology examples are given in the. So now these are buck converters, three-phase buck converters. So you can have a comparison table in order to compare the different topologies. What will be the overall price? What will be the rating of the switches? And what will be the size of the equipment if I use that particular topology? All these things you can, all these parameters you can use to decide what kind of equipment you want, or what kind of topology you are going to use for your application. Then there is three-phase unidirectional or bidirectional buck boost IPQC. So we discussed boost, buck and buck boost. So all these topology examples are also given. Then certain numerical problems are given in order to give you a gist of what these converters can do. And there are multiple AC to DC converters. They are discussed. So as I mentioned, if you increase the number of pulses, then within the same phases you can increase the number of pulses by increase the number of switches, and when you increase the number of pulses, then the ripple reduces, and therefore we obtain closer to a pure DC waveform. Therefore these were discussed. Okay, so these are called multi-pulse converters. So we have already solved few numerical problems of 12 pulse converters, right? So similarly, we have 24 pulse converters, 16 pulse converters. They are used in high power applications like AC/DC motor drives, high frequency welding equipments, HVDC systems, and air furnaces. So these are the applications of these multi-pulse converters. So we have 12 pearls, 18 pearls, 24, 30, 36, 42, 48. So there are tables given in order to give us an idea of the comparison. So if you look at the percentage THD, then you will observe that for 6 pulse converters you have 31% THD, and as you increase the order, these THD gets on reduced 15, 10, 7, 6, 5. So depending on how much more cost you are willing to give, and how much more pureness in DC waveform do you desire. So based on that you can decide which type of converter you want. Then there is classification of multipulse AC to DC converters. Then in the classification, these three-phase multipulse converters are categorized into unidirectional and bidirectional category. Then these converters are categorized into isolated and non-isolated, and these isolated and non-isolated are categorized into full wave, bridge, and bridge type of converters. Now a lot of topological examples of these converters are given, and also isolated versions of these converters are given. Now since I mentioned that multiples might be used in high powers, so whenever high powers are involved you need to go for isolation. So these are different topologies where different isolation transformers are used, either zigzag ones are used or T transformers are used, or double double star, double delta. These technologies, different kinds of T type of transformers. So these are a lot of complicated combinations. But if you try to understand the basics behind these, you will be easily able to understand what is going on. Okay. And then there is delta, zigzag. Lot of topologies are present. Okay. So these are the comparison tables of these converters. And then after talking about the multi-pulse converters, there is these are the classifications. So you can observe here, right? Lot of type of transformers are present, and these are only few. So apart from that, the basic thing you can do is you can try to understand how they work. So once you know about the one type of topology, it will be easier for you to understand the others. So let us move on to the last topic for today, that is power quality improvement in solar energy conversion systems. So when you now we all have been making a big fuss about solar energy. We already discussed, right, that why we need solar energy. We our
Madam,
non-renewable
voice is some disturbances, madam. Voice is not clear, madam.
not clear. Okay, just one
Voice.
second. Am I audible now?
Okay, madam. Now, okay, madam.
Okay, okay. So when you talk about solar energy, we know the motivation behind solar energy, right? Our the non-renewable sources of energy are depleting, and then there is we want green energy. There is global warming, so we need more and more renewable sources of energy. And because of that need, recently even government and everybody is pushing solar kind of solar energy, right? So therefore, we are moving towards using more and more of solar energy. And uh, currently 75% of our electrical power is generated by burning coal, which is very bad form of energy, right? And nuclear power plants, which is very dangerous. So we need to replace this major chunk of non-renewable energy with the renewable ones. Therefore, there is a huge push for increasing the solar power consumption. Now, power quality issues in grid interfaced solar PV power generation. So when you connect our grid with solar PV, what happens is there are few problems, technical problems that come into picture. Some are voltage fluctuations, harmonics, DC offset, high frequency waves, reactive power, voltage regulation, low power factor, unbalanced grid voltage, neutral current compensation, solar power intermittency, load management. There are a lot of problems that come into picture when we connect solar to the grid. It's not that simple, right? Everybody just tells just put solar, right? But it is not never that easy. You have to look at the consequences of doing that, and there are a lot of problems. So now again, as we discussed in the starting of the lecture, there are two options available to us. One is I could put a separate shunt compensator or any kind of compensator for improving the power quality. Or another thing I could do is there is already an inverter present which is converting the DC from solar into AC. There is already a converter. So I could use that converter which is present there for serving these purpose. So that converter will be called a power quality improvement converter, or IPQC. It will come in the category of IPQC converter. So therefore, grid connected solar PV rooftop systems, if we talk about, they are very small in scale, and they are put in residential, commercial and industrial areas. So nowadays, if you talk, then every other home in, especially in South, has a rooftop solar, and industries are very much encouraging the deployment of these solar rooftops in their arenas. And then electricity generated could be fed into the, so if you are having very little amount of energy generated, you can use it for your purpose. And if you are having very high amount of electricity that is present with you, you could use it for the purpose of pumping it back to the grid. Then there are a lot of advantages of rooftop grid interface PV systems. You could have savings in the transmission distribution losses. Basically, if you use solar, you just have to pay for the initial investment cost, right? Once you have deployed that solar plant in your house, you won't have to pay for the electricity. In fact, if you are pumping into the grid, you will get back the payment. That means you might start earning if you are having surplus power generation. So that is actually like most of the people with whom I have talked practically, they have had very good experiences. They just have to take care of proper maintenance. So you need to clean the panels from time to time. You need to, take care of the electrical equipments. That like there might be a battery inverter, or you might have to just do little maintenance. If you are able to do that, then you can have, break even point. Basically, the cost, whichever how much amount you are putting back in these systems, you will in 1 or 2 or 3 years, you will be able to, get back that money. You will have a savings in your electrical bills, huge savings. And then later on, once your initial cost is, break even, then you can start earning money using that panel, right? And the warranties, or if you talk about Indian panels, then the warranties of these panels are in the range of 10 to 15 or 20 years. So you can easily, run the same panel by maintaining them properly for such a long duration of time. So therefore, these are the advantages of these type of rooftop grid interface PV systems. They have low gestation time. In a duration of a few months, you can easily, apply put these systems in your rooftops. Then there is no requirement of additional lands. We all have our terraces, right? Most of the people put them on the terrace, or some people put it on the there is this overhead tank, right? Overhead storage tank, some people put it there. So then improvement of tail end grid voltages. So we all have been talking about, the non-linear kind of load. So what we discussed is that whenever you are drawing, even a small amount of non-linear load at your home, what is happening is it is going to the distribution system, that non-linearity, and then this non-linear current is making the point of common coupling voltage also non-linear in nature. And if we start generating our own solar energy, then we are solving that problem, right? We are taking the energy that we are generating, so we are not transmitting any nonlinear current to the distribution or transmission system, right? So that we are helping the grid in this case. Then it is generating employment for local people. There are a lot of startups who have started doing the rooftop solar thing, and your definitely your power bill will reduce, especially in summer when you are getting double or triple amount of bills. Then you can definitely reduce them. So, and if you are eliminating the battery, if you are fine with not having inverter during the power cut, then also it's very good for you. You will have a lot of power saving, and you won't have to maintain the batteries. Then there are no storage losses present in this system, and then you are easily able to maintain the power quality of your house. There is a security of supply. You won't have to depend on our traditional electricity suppliers. So if you are in a village, and in a village, in a day, there are still villages in India where electricity supply is not available for more than 5 hours. There are villages in India right now. So in villages like those, solar rooftop and microgrids are a very good idea, because instead of trying to provide electricity connection to those villages, it is much more easier and cost effective to install a local microgrid there. And they have a lot of land, right? You can just put a lot of solar there, and then you can easily give them electricity. And they won't have to you won't have to connect a lot of long wires to give electricity to them, and it will save a lot of cost. So performance verification can be done. Then indirect cost reduction happens by reducing the losses. Energy storage elements are not leached. Load profiling starts flattening, because we all will start generating our own energy. So this is an example of rooftop solar, where this is suppose you are putting a rooftop solar panel on your terrace. So you will have certain protection devices. There are protection diodes and all these things. Then there is junction box. At this junction box, you will connect or there will be a lot of panels, right? They will be connected in series, and then those panels will be connected in parallel, and then those overall strings will be brought to the junction box. Then at the junction box, we have a net DC output voltage, and then using that, this inverter, we will convert that DC into AC output. And then I'll put an isolation transformer because I don't want my system to get damaged or any of my electrical equipment to get damaged in case of lightning or any kind of fault that might occur in the solar panel. So isolation is always better. So I'll put an isolation transformer. Then I could, if I want, I could give a manual disconnection option there, or I could directly connect it. So I have an option to feed this power to my house, or I can give it to the grid, or I can do both. So it will depend on how much is my generation and how much is my consumption. So based on that, we can do the analysis of whether we want to give to the grid or we want to keep it to ourselves. So if you look at the classification of solar energy conversion systems, then they can be classified broadly in the category of standalone and grid interfaced. So if you have a solar energy rooftops at your place, then you could either use that solar energy, small rooftop for fulfilling your own electricity requirements, or you could use that and pump it back to the grid. So whichever you want, whichever is much more feasible and cheaper solution for you, you can go for it. So there are two basic classifications. And if you talk about grid interface, then you could interface it either to a single phase grid, as in the case of rooftop normally we do, or we could interface it with three phase, which we do in the case of solar parks. So for single phase, you could either do a single stage connection or two stage connection. Single stage and two stage just means that you could, if you have a DC, you could connect it first to a DC by using a buck or boost converter, and then you could use a DC to AC converter. So that is a two stage converter. And if you are converting that DC directly into AC, it is a single stage converter. That means how many cascading converters are present in the way. So based on that, we can classify it into single stage and two stage converters. Then single stage and two stage converters
And
can.
better to connect a two stage converter, madam, or one stage converter, madam.
No, sir, single
One.
stage is always better because if you have this input, let me call this as stage 1 and this is stage 2, and this is my output, and another is input, and this is stage 1 and this is output. Now you tell which one will be better.
Cost point of view, second one is better, madam.
Yes.
But quality point of view, if you want to more quality output, then you have to provide two stage converter, madam.
No, sir. Like the quality means you can talk about the pureness of the DC that you're getting, right? Or you could talk about the power factor correction that you're able to achieve. With the advancement of the converters and the technology, we are easily able. There are like in we were just discussing, right? Initially, we had diode bridge rectifier, then we had boost converter, then we had output. Instead of that, there were topologies which had bridgeless converters. So if my bridgeless converter is able to give me the same output that I am able to get without with the bridge, then definitely I'll go with the one which has less components. This will be cheaper and most effective. And another reason we don't prefer multi stages is because of the law. So there is always losses, right, in these systems. So if I tell you numerically, then if my system is operating at 90% efficiency and these two are operating at 90% efficiency, then the net this system will have a efficiency of 90%, and this cascaded system will have an efficiency of 90% into
81%.
90%, right? 81%, right? Because they are cascaded, so they are like basically they are series connection, right? So the efficiency of this will be multiplied with efficiency of this in order to obtain the overall efficiency, that is output by input, right? This is output and input, so it will reduce to 81%, which is less than 90%, right? Then therefore that is the major drawback of having multi-stage thing, that it reduces the efficiency of the system. The cost is definitely, that will also definitely be higher. Okay, is it clear?
Okay, madam. And if the stage one is sufficient, why you have to go for a stage two, madam?
No, actually, so whenever you start developing, now what happens is, suppose somebody tells me that I need a fixed DC, I have a DC supply and I need to make AC supply. Then what I can do is I can think of multiple ways, right? I could convert this DC into variable DC, then I could put an inverter that will convert this DC into AC, and then I can step down this AC and obtain. There are a lot of ways possible. So people have just come up with different topologies, and surprisingly, there are a lot of applications in which even multi-stage might be of use. Suppose I have a circuit in which diode bridge rectifier output is already present. Then instead of putting in
And
additional
generally,
diode,
solar two-stage conversion is used, madam. Solar like intermittent nature.
so I think I practically I don't know which one are used, but if you go for I think solar two-stage ones are cheaper and they are bulky in size. So whenever you want a very compact type of inverter, then you will go for a single stage, but it will be costly. So if people want cheaper ones, then they go for two-stage, I guess, because two-stage mein you already have commercially available diode bridge rectifier bridge, right? So I think for manufacturing purposes, it might be cheaper. Therefore, people might be still using. Also, when you so there is a huge timeline gap between research and industry. So the thing that we are studying in academics today will come in industry after a few years. So if I am developing a new concept today on 17th April, then it will come in industry after few years. Industry will have to find the need of that thing, and then industry will have to convert that a proof of concept into a product. And there's a lot of engineering that is required in converting just a theoretical concept into a product. So that takes time, and they need strong motivation to do that much work. They need to put a lot of money, right, for R&D in order to make a new product. So until there is a strong need, or until there is a strong saving in cost, or there is a strong customer base, they don't go for that. So if two stage ones are present in the market, they might keep on existing until 50, 60 years, until maybe there is 50% reduction in cost now. So some new player will come in market, it will start selling the single stage one, and then the two stage ones will also start investing in the R&D, and that is how it goes. So industry normally it's very slow and it's very old. So they do work only when it's required, when there is significant advantage that is available with any new type of adaptation. Because from their point of view, if you look, then they have made full any equipment that is developed in industry is first step by step assembled. Then you have to do proper testing, then you have to get them certified. So there is lot of things, full channel you have to make. Then redoing that again takes a lot of time and cost. So until unless it's necessary, they don't do it. Okay, so if there is no if additional benefit and cost is not there, then they will not do it. So therefore, sometimes there it might be possible that the two-stage ones might be cheaper because they are manufactured by a big player in the market, and single-stage ones are costlier because they are very manufactured in very less units. So that might be the reason of the popularity of two-stage ones. That also happens. So you cannot always make a blank statement when it comes to, because that there is a rule that if you increase the number of equipment production, then you can reduce the cost, right? So that rule always changes the what we think and what actually happens in the market. Okay. So in the lecture, so this is the PV array plot. So this is the power versus voltage curve, and this is current versus voltage curve. So if you look at this current versus voltage curve and this power versus voltage curve, there is a peak power point, right? This is the peak power point in this curve. This is the peak power point in this curve. So what happens is there is always this. So if I am doing a job and somebody is giving me 100 rupees and another person is giving me 90 rupees, then I'll always try to gain as much as possible, right? Similarly, in energy, if I am getting 100 watts here and I'm getting 90 watts here, I'll definitely try to get 100 watts all the time, right? I want to increase the efficiency of my system. That is the goal. So I put a special algorithm in my converters in order to track this maximum power point, and I make my converters operate at this maximum power point. That is called that algorithm, any kind of algorithm which helps my solar PV system to operate at maximum power point is called maximum power point tracking algorithm. And there are a lot of these type of algorithms that are available in literature. Few of them are hill climbing, perturb and observe, incremental conductance method, fractional open circuit voltage, fractional short circuit voltage. All these different methods are present in the literature, and the main goal of all of these is to track this maximum power point and operate my system at this maximum power point.
What is the maximum power point tracking, madam?
That only, na sir. I just explained, right? That this is the power versus voltage curve. This is for particular amount of light that is falling on my solar panel. This is the peak power point, right? In this curve, this is the peak most power that I can get. So why I don't want to take less power. If I can get more power, I would always want to get more power. Therefore, there is an algorithm that I put in my controller in order to detect this point. And after detecting this point, I operate my system at this point. I try to
Yes, it is
con-
helpful to design that solar panel, madam.
no, it is not
Going to
helpful to
analyze
design
like
solar panel after you obtain the solar panel output, you put these MPPT controllers in the converters that are present there. So if you talk about this maximum power point, these maximum power point is corresponding to a particular voltage, right? Let me call it as Vm. So if I plot this Vm in this curve, then there is a particular Vm and particular Im here, right? So I will put a closed loop, and I will using the closed loop control, I will draw a significant this Im amount of current from my solar panel, so that I operate at maximum power point. That is the goal.
okay, okay.
Okay, so you can look at the lectures in detail. So there is Umanand sir's lectures, L. Umanand sir's NPTEL lectures on MPPT. So he has very nicely explained. Okay, so you can just watch one. It's I think it's a 15-minute or 20-minute lecture. Very simple. Just go through that. Or if you don't want, you can. I did the tutorial for that course also. So on the same YouTube channel, those lectures are also available. So you can watch that. But sir has explained very nicely. Like I am still learning. So if you want a concise version, I have put a concise version of that in my YouTube channel. And if you want just search version, then you can just search on YouTube. That is a solar PV course by L. Umanand. So in that there is one lecture which is titled maximum power point tracking. So he has very nicely explained with simulations and everything. So you will get a very nice gist if you are not clear with the concept. But basically what we are trying to do is we are trying to operate at this maximum power point. And how do I do that? I know that there is Vm amount of voltage and Im amount of current corresponding to this maximum power point, and I do a closed loop control in my system in order to operate at this Vm and Im, so that I can get maximum power out of my solar panels. Okay, so these were few of the techniques that were available in the market. So in the next class, we'll be discussing about a few solar conversion system problem, and also we'll be discussing about wind energy conversion system problems. Okay, so that will be the content for our next class, and I hope you all are you all are prepared for the exams.
Do you have any meta scripts related to this power quality, madam?
MATLAB.
Scripts, madam. Any?
Scripts, I haven't made that many scripts so far. Just the basics ones only, like basic computation ones. Mostly, so this was a new course for me also. So this course does not exist in ISC. So I have done MATLAB simulation for simple power electronics, but not power quality specifically. And we don't have the time also to take that depth. Sorry.
Okay, madam. Is there any possibility, madam? You will be posting your channel, madam. Is there any possibility?
Yes, that I can do. In future, if I do any kind of simulations, then I will definitely try to update on that channel.
Okay, madam.
Okay, okay, sir. Okay, guys, then we'll wind up today's session.
Okay, thank you, madam.
Okay, thank you.